Hello. When you go to a website and you try to search something and you type in some letter, the search panel suggests you some word based on the letter you have typed. How did you ever try to wonder how the search panel knows that which word to suggest you to? Well, try data structure is behind that. Say you have say you have typed A, L, then G. The search panel will suggest you these three words based on your search terms. Why? Because all of them have ALG on top of their name. How does it do that? Let's try to learn that. So first there will be some nodes to store these letters. The first one will be the root node. This is the starting point of every kind of tree data structure. This is our root node, and the program begins here. Now, say we want to write in the word algo. So what is the first letter? A. We come to the root node and check if there is any age pointing towards the letter A. We see that there is no age pointing toward the letter A. So what we do, we add an age. We add an age and we add a node. This age will point as the letter A. Our first letter is done. Then we go to the next letter, L. We come to A, which is our current node. This is our current node, and we try to see if there is any age pointing towards L. We see that there is no age pointing towards L, so we add a new age named L. Our second letter is done. Then we go to the next letter, G. Same thing, we change our current node to this node. We check if there is any age pointing towards the letter G. No, so we add a new age, G. Then to the next letter, O. The current node is now this one. We check if there is any age pointing towards O. We don't find anything, so we add a new age named O. Now what? Our letter is finished. Our word is finished. We don't have any letter left. So what we do is we point this O node towards null. Our first letter, algo, is finished. Now let's move on to the next letter, algae. The first letter is A. We come to root, we find that there is an age named A, so we skip it. We move on to the next node, we move on to the next letter, L. We see that age A is pointing towards the letter L, so we move to L. Then we move on to the next letter, G. We find that we also have G, so we move on again. Now the letter is E. We come here and we find that there is no age pointing towards the letter E. So what we do, we add a new node, and the age is pointing towards E. Then to the next letter, A. Again, the age A is empty, so we add a new age. and a new note. Our word is finished, so we add null to it. We finished writing these 3 words. Now let's move on to 2. We go to root, we check if there is any h pointing towards t. No. We add a new h. Then the next letter O, and the word is finished, so we point it to null. Then the next word, Tom. Same, T and O exist, but after coming to O, we have a letter M left, but the O is pointing towards null. So what we do is we remove this null, we add a new H named M, and point towards a new node, which then point towards to null. Our formation of tree data structure is completed here. Now we want to search a word in this using this data structure. Let's say we want to search the word algo. We first process the letter A. We go to root. We say there's a age pointed towards A. So we proceed. We then take the next letter L, and we see that we also have the letter A, the age pointed towards L, and we proceed. This way, ALGO, we find all these letters, and after reaching O, we see that the age O is pointing towards null. After reaching O, we see that the A node O is pointing towards null. So we presume that the letter algo exists in this tree. Then we take another word. Say we want to find the word alive. What we do, we go to root, we check if A exists. It does. Then we move on to the next node. L, does it exist? Yes. Then we try to move on to the next node. Does I exist? No, I doesn't exist. So it exists. But what if we try to find something that has some prefix match in the tree? Say, just for example, say we want to search a letter, a word that is named ALG. It finds that A, L, and G, all these 3 exist in this structure. But does this word actually input in this tree? Actually, no. Why? How do we know that? Is that because the age G is not pointing towards any null pointer. It's pointing towards a new node. So ALG does not exist in this place. So what we know from here is that the last node have to point towards a null value, so to determine that a word exists in the structure. But is it final though? This thing brings us to a new issue. Say we want to search the word to in this place. We come to root, we find T, we find O. The word is finished, there is no new letter in the word, but the node O is not pointing towards any null value. So does a 2 does not exist in this place, but it does. Why? How do we know that? Because we did put the word to in this tree, right? So what do? We introduce a new term. We introduce a thing called flag or color or whatever you want to call it. See, it might happen that some words just have more extension, and if we always try to find a null value, in this case, we will not be able to find 2 in this place because 2, the age O does not point towards any null value. So what would we do is that we can add a color. For example, when we took the input of 2, after O, we will color it with a different color, something to determine that this word exists here and it ends in this node named O. So every time a word ends, we will color it with something different so that we know that the word ends at that exact node. So now when we try to find the word to now we go to root, we see that T exists, we see that O exists, and O points towards a node that is colored with a different color. As we have found that, we can determine that 2 exists in this tree. So our next condition will be that each node will have a flag color value. This is how tree data structure works. Let's try to create the code for this Trie data structure. So at first, what we need some nodes, and we need some age to point towards another node. So let's create a struct node. Now we can leave it like this, but what will be the size of the age? Is it that the root will only point towards A and T? No, there can be a lot of words pushed into the root node. So we need an array of letters. So we will create an array of ages, and what will be the size of the age? As we are working with letters, so there are 26 letters. The size of the array age will be 26. And the next thing is, see, we have to color every node to determine whether a word ends there or not. So add a boolean named flag. Now we have to initialize the node. We add a node constructor and we add flag equals to 0 for all of the node initially, and each age has to point null at the start of the trie. So for int I equals to 0, I less than 26, I plus plus, and age I equals to null. Now what does it do? What does this thing do is that it initializes a tree, and it points every single letter to null before we add anything to the tree itself. Now we have to take input for the insertion. This will determine how many words we will be taking, and we'll initialize a new node. Named root, so that we can start from here. Then we take input for the words we want to push into the tree. We will be pushing this word into the tree. So take input for the word. What we're doing is that we're trying to push the root node that we have created here and the word we have taken in each for loop into the tree. Let's create the insert algorithm, insert code. Void insert. The parameter will be word and root. What will be the data type of the word? What will be the data type of the root? It will be node type. So string word and node root. Every time we enter inside the tree, we always change the current node. So at first the current node is the root node, and after pushing to A, we find the current node is the L node, and so on. So we have to create a new node named current node. And we have to determine the length of the word so that we can use a for loop on it. Word.length. Then we create a for loop. This loop will work to the length of the word Now inside the for loop, we have to check. Say we want to push the letter A. We have to check if the letter A is pointing towards null or not. So we have to check if it is null at the if statement. If current pointing towards age word I is equals to null. So what does it mean? That the age of the current node and the word I, meaning the first letter of the word that we have taken, whether it is pointing towards the null. If it is pointing towards null, it will get into the if statement. The current age word I equals to new node. So we have checked that the age of the current node is null for the letter I. So we have created a new node for the letter I. And now we are going to push the current to the new age. So what it's doing here, after taking the A as a new age, it is pushing the current node to the L. If the for loop ends, we will change the flag color to 1. What this means is that whenever we are finishing a word here, here, and here, all these places, we are going to change the color of the flag to 1, which is primarily 0. Now, here's a problem to address. See, we are taking the letter A, L, G, etc. The value of A in ASCII code is 97. See, the problem is that our array initializes at I equals to 0, 1, 2, etc. But the letter A is starting from 97. So what we have to do is that we have to subtract 97 from each of the array input. So if we subtract 97 from 97, it's 0, and it will denote A. The ASCII code for B is 98. So after subtracting 97 from 98, it will remain 1, and it will point to B, and so on. So in this place, we have to subtract the letter A. Each time we are working with the index I. Now we're fine, where our insertion is complete here. Okay, insertion is done. Let's go for searching a word in the tree. Let's type in a new line into the word to search. Now you might ask me, why did I write search 1? Well, I don't know about the C++, but writing normal search creates issues, and the code doesn't seem to work properly, so I just wrote search 1. Okay, if search we will create a function named search. It will return yes or no. If the function returns true, it will print yes, and if it doesn't, if it returns false, it will print no. Let's move on to create the search function. Bool search, we're going to push the parameter word and root type node. As we have seen before, we are going to create another current node equals to root. Same goes for, we have to create a variable L for the length of the word. Create a for loop to iterate through the letters of the word. Create a variable named index equals to word I minus a. You can do it like in the previous way where I directly subtracted the letter a from the word in the if statement, but you can also create a completely new variable here. Just as it was an insertion current age, the index that we have created here if it is equals to null, in this case it will just return false because it means that the letter does not exist here in this place. So if I go to root and I search for the letter A and I find that the letter A does not exist, it will just return. And if it is not the case, if the if statement is not true, then it will push the current age to the next age. What this will do is that if it finds A, then it will push the current age from root to the current age L, and so on. If this for loop completely executes and it does not return false at any given point, it means all the letter of the word exist in this tree. It will then return current flag. Remember flag? It was actually a boolean, right? So it is always 0 or 1, which means it is always either true or false. So after finishing the for loop, it will check if the word has finished, which means if the flag is 1 or 0. If the word has finished, say if I'm searching for algo and it reaches O, where the flag is 1, means true, this statement will return true. But if in some case, if I have searched for ALG and the G is not colored as true, this will return false. So coming to the main statement, if this flag returns true, it will print yes. If this flag returns false, it will print no. So let's run the code. It will take two words, hello and bye. If I want to search the word, say if I say, again search the word hello, it will say yes, so hello exists in the tree. Let's run it again. Two words, hill and hello. Let's search for hill. Does hello exist? Yes. In another case, hill, hello. Let's search for he. He does not exist here, although he is a prefix for some of the word in this tree. So this is how we can implement trie data structure.